Hello and welcome to today's AP Chemistry stream featuring Gibbs Free Energy. Um, Hi guys, how are we? How are we coping with quarantine? I'm starting to go a little crazy. Good evening. It's 10 a.m. Isaac. 8.5 out of 10. That's actually pretty high, Max. That's not bad for coping. Yeah, Maggie, you especially because you guys are like really quarantined. Um, Most people can still go out and do stuff, but yeah. Hello, Isabel. How are you? Reorganizing your room. That's a good plan. Ring and jewelry. That's a good thing. Yeah, that's something to do. 3:30 a.m. Oh, that's late. Man, you guys need to go to bed a little earlier, at least like 1 a.m. But Max, you can though. Like, uh, you can only do stuff for so long. It's just such a disruption to the normal routine. We'll see if TJ joins in, Mikey. Who knows? Honor kids this morning were like, ugh, they were something else. I had to ban a bunch of them. Gotta get that Fortnite dub, Logan. Um, Sammy, I might have time today. I don't think the notes will take the whole 40 minutes I have planned. So I can do maybe one or two of them. I do like waiting and having more of that one-on-one time later. But yeah. So no, I should have some time to do maybe one or two of the homework problems today on the stream. So that'll potentially help. Okay, what else we got? What other questions? Yeah, that might be something to do, Naya. I mean, you guys still have a lot of stuff to do, but not being able to leave your house makes it so you just kind of stuck. I'm doing okay, Isaac. I just this week has been crazy. It's felt like forever just being so busy with everything, getting these streams ready, teaching. Teaching on those streams is different than teaching in class. Mostly because I've been teaching in class for like 8 years. Yeah, they're they're getting they're in the bath right now because they were painting earlier and so they got paint on them. Well, at least you got your chemistry stuff done. Yeah. Yes, Isaac. This week was spontaneous in the colloquial definition, not necessarily in the chemistry definition. All right, we'll wait till a couple more people join in, and then we'll dive into some questions from yesterday. Definitely disordered. Yeah, definitely definitely an increase in entropy. Hey, an hour of homework a day is probably mostly what you need to do, Naya. So, as long as you stay caught up, you should be good. Oh, 10 a.m. to 11 p.m. That is a very that's a much larger window. Um, yeah, the Contagion movie is a pretty cool movie. I don't know if you guys have seen this infographic. Johns Hopkins has a really good one. It's the one that a lot of people are using. Johnny, don't make me ban you. All right. So the Johns Hopkins ones is really cool because it shows kind of all the worldwide cases and all the things that we've got going on. Oh, I've got a big delay. So the cool thing is on the Johns Hopkins ones, it jumps up really high, and it shows all the cases. We're up to 173,000 cases. Yeah, it really does look like Plague Inc. It's kind of crazy how much things are looking like all those epidemic or pandemic games that people play. Okay. Um, let's see. What other questions do we have? What other things are going on? Sorry, I lost the chat there. Yeah, I got it. Thanks, Isaac. Okay. What else? All right. So let's go ahead and dive into any questions from yesterday. So any questions from understanding delta G naught, all those things. Where are we at in terms of holes and things? Oh, so Sammy, that's a good question. So let's talk about S and delta S. So entropy, S, is just a measurement of how much randomness or disordered is in a given substance, kilojoules per mole. Or actually, sorry, joules per mole Kelvin. It depends on temperature, it depends on a lot of things. When we talk about delta S, that's how does entropy change over the course of a reaction. So delta S, we're going to take our products minus our reactants, multiply by the coefficients, and that'll give us the change in entropy for a reaction, whereas just plain old S tells you how much entropy is in a substance. So a given particular element or compound, how much entropy that substance has per mole per degree Kelvin. So delta S is for reactions, S is for specific substances. Hopefully that helps. Yeah, so Maggie, it's really in terms of like physical meaning. Gibbs free energy doesn't actually have a physical meaning. You can kind of think about it as leftover energy, but it really just is a measure of the degree to which a reaction favors the forward direction, right? If it's negative, the more negative it is, the more forward the reaction's favored. In terms of a quantity, it's not like something you can pick up and measure. It's more so like the potential to react. So it's more. It's almost like a potential energy idea, but even then, it's kind of a trick. It measures how spontaneous a reaction is, which is all, unfortunately, the most details I can really give on it. I think so, David. I'm trying to remember what your question from yesterday was. Oh, why are the units kilojoules per mole? I think was your answer, or was your question. Yeah, so that's kind of your answer. It's just a measurement of potential energy and things like that. It's one way to think about it. Yeah. Okay. Oh, Mary. Oh, you're asking the hard questions. No, it doesn't. Um, which is a little interesting. It's tricky that oftentimes spontaneity and rates, so thermodynamics, like the energy associated with a reaction, and the rate of reaction, how quickly a reaction goes, are two different ideas. So just because something is really spontaneous doesn't mean that it's going to have a high rate of reaction. They're separate ideas that mean chemistry teachers will often try to get you to get tripped up on. Isaac, let me pull it up to make sure I know what you're referring to. It might ask, I think it asks about both. Yeah. So the assignment sheet, the first problem is just asking about rates. The reason you need the delta G information is to calculate the equilibrium constant. So there's a rate question on part A, and then there's a, so remember, because we're getting to the end of the course, so this first part, this part A, is a throwback to previous chapters, right? The part B is what's really from this chapter. And so again, as we get towards the end of the course, we're going to start asking more all-encompassing questions, more things that pull back from previous chapters. And so, yeah, this is whoever wrote the 1975 AP test was having a little fun with this question. Yeah, so the part A is from previous chapter, the part B is from current chapters. All right, let's dive into what we want to talk about today. The test, Isabel, it's going to be pretty similar to the chapter 15 quest. I'm just going to post it online. Isaac, you just hate everything. I'm gonna post it online. You guys will just take it online and do kind of the same thing that we did for the chapter 15 one. So, okay, let me grab minutes. So yesterday we did Roman numeral 2. What does the not mean? Values of delta G. And give an example. So yeah, so that was, let's do letter C. Okay. Letter C. Non-standard conditions. All right, so for our non-standard conditions, what we're really meaning here is we're saying that the pressures do not equal 1 atmosphere and the concentrations do not equal 1 molar. Right. So remember, our idea with when we're talking about the not in delta G naught, that not meant that all of the pressures for the gases were at 1 atmosphere and all the concentrations were at 1 molar. And so if our pressures are not at 1 atmosphere and our concentrations are not at 1 molar, we're going to do we're not going to go fully through the derivation of this, Isaac. But the equation that we get out of this is that delta G equals delta G naught plus RT ln of Q. Okay, so this is our standard conditions. This is our non-standard, right? No, Naya, volume doesn't matter. It's just RT ln of Q. So the R here is going to be our joules R. Actually, we probably want it in kilojoules. So it'll be 0.00 831 kilojoules per mole Kelvin. And then T, of course, temperature in Kelvin, right? And then Q is our Q. It's, the concentration of A to the A times the concentration of B to the B, concentration of C to the C, right? It's our equilibrium constant expression Q for our non-equilibrium conditions. Okay, sorry, that handwriting on that's really bad. But yeah. So what we can do is we can use a standard delta G to calculate a non-standard delta G. So yeah, if we had gases in the equation, it would be pressures as well, Isaac. Yeah, that's a good point out. I just use concentrations because we spent so long doing acids and bases and things. Okay, so let's do a quick calculation here. Let's do some examples. So first, I want to find. So let's find delta G naught using delta G naught of formations. All right, so if we look at the reaction, PbI2 solid breaking apart into lead ions and 2 iodide ions. Okay. Normally, kind of up to this point, if I wanted you to find the delta G for this equation, you would look up the delta H of formation values, you would look up the entropy values, the S values, and you would sum the products and subtract the reactants and go from there. If I want to know it at 25 degrees C, we can use page 601 in the text. Joel, there will not be ice tables as far as I can remember. All right. So if we look at 601, okay, if we look at 601, reminder, we have our delta H of formation values, we have our S values, but then we also have this delta G of formation at 25 degrees C. So again, these values only work if we're at 25 degrees Celsius, because if not, we would have to calculate delta H and delta S for the reaction and plug in the temperature if it was other than 25. But if we have a reaction at 25, we can use these delta G values to save us some time. Okay, so what I'm going to do is I'm going to look up the values for PbI2 solid, Pb2 plus, and I minus. So that's actually on the next page. So PbI2 solid. Oh, of course it's not actually in here. Oh, dang it. It's a long week. Okay. Let's not do PbI2. Let's do PbCl2. So, scratch this out. Go to the next page. I needed more room to do the problem anyway. Let's look at lead chloride. Okay, so if we look at the delta G naught of formations at 25 degrees C. So now we can find the lead chloride is negative 314.1. The lead ions are negative 24.4. And the chloride ion you can get a timeout, Xander. All right, so the chloride is negative 131.2. All right, so to find the reaction, right, we're going to do the same thing we've always done. We're going to get the, so the delta G of the reaction is going to equal negative 24.4, I should include the units, kilojoules per mole, plus 2 times negative 131.2 kilojoules per mole. All of this minus negative 314.1 kilojoules per mole. And sorry, this is delta G naught. So delta G naught of the reaction. So now we just do the calculation. So negative 24.4 plus 2 times negative 131.2 minus a negative 314.1 gives us 27.3, a positive. Okay. So what does that mean about this reaction under standard conditions? Yeah, it's non-spontaneous, right? Because delta G is positive, means my reaction is non-spontaneous. And we know that, right? If we had 1 molar lead and 1 molar chloride, it would form the solid. It wouldn't keep dissolving because lead chloride is an insoluble ion. And so this positive delta G makes sense from what we know about KSPs and all those things, okay? So what if, right? What if the concentration of lead was 0.0010 and the concentration of chloride was same thing, 0.0010 molar. Right? Will the reaction be spontaneous if we have this? So it kind of is an equilibrium, Sarah. I drew it as a forward arrow because that's what we're trying to calculate. We're trying to calculate, will this be spontaneous in the forward direction? But technically, it might be more appropriate to draw it as an equilibrium arrow. Okay, so what we're going to do to answer this question is we're going to use the equation we wrote down previously. That delta G for my non-standard conditions, right? If this is 0.001 molar and this is 0.001 molar, Isaac, I thought about getting a whiteboard, but I actually really like paper. I like the feel of it better. Yeah. Anyway, so delta G equals delta G naught plus RT ln of Q. So what we're going to do is we're going to find, all right, well, what is our delta G at non-standard conditions? So we'll plug in the delta G at standard conditions, the delta G naught, and so we get the 27.3 kilojoules per mole plus my R, 0.00831 kilojoules per mole Kelvin. Temperature, I said this previously, but to reiterate, we are at 25 degrees C. So this is going to be 298 Kelvin. Okay, and then it's the natural log of Q. So what is Q, right? So Q, reminder, is our products divided by reactants, coefficients turned into exponents. So because the lead chloride is a solid, it doesn't appear in the Q expression. And so we just take 0.0010 times 0.0010 squared. Okay, our lead concentration times our chloride concentration squared. And so now we just plug this all into our calculator and see what we get. I'm going to evaluate this a little more piecewise. So I'm going to do all of this together. So let's do 0.0010 basically cubed the natural log of that times 298 times 0.00831. So this turns out to be negative 51.3 kilojoules per mole. And so then the sum is negative 24. So the sum is negative 24.0. Okay, what does that mean? What did we just find? We plugged in all these numbers and we calculated something, but what does that tell us? Yeah, Sarah's got it. It's spontaneous under these conditions. If our concentrations are much lower than 1 molar, this lead chloride will dissolve to make more lead ions and chloride ions. And so it turns out that this Q had a big enough effect on my delta G to where it made it to where it becomes spontaneous. We get this negative, okay? Good, a lot of people are chiming that in. Cool. Now, what we can also do is we can also use this equation and this idea to solve for K. And that's our equilibrium constant K. Let me show you how we would do that. So I'm going to keep on this lead chloride equation. We're going to solve K in a second here. But are there any questions before I move on to do that? Yeah, Maggie, that's actually a really good observation. So if Q is less than 1, that makes this whole term turn negative, which means that our delta G under these conditions will be less than the delta G naught. If Q is greater than 1, this whole term turns out to be positive, and so then our delta G will be a larger value than the delta G naught. No. If it's positive, it's non-spontaneous, Lauren. Sorry. The positive here makes it non-spontaneous, and then the fact that delta G down here is negative makes it spontaneous. So that means, so Joel, to answer your question, it means that if we had solid lead chloride and our lead and our chloride concentrations were as such, that more of it would dissolve. But remember, as these concentrations change, so does delta G because Q is changing. But under this exact freeze frame moment in time, more lead chloride would dissolve. Okay, let's talk about how we can find K. So we're going to keep using this equation. So I'm going to rewrite that equation one more time. What number am I on? Sorry, I'm a little all over the place today, guys. Let's do number 4. So if delta G equals delta G naught plus RT ln of Q, okay, what if we wanted this Q to be K? Right? What if this Q was the equilibrium constant K? What did we say happened to delta G when we were at equilibrium? G equals 0, right? Now, not delta G naught, but G. So our delta G, we're going to plug in as 0. So delta G equals delta G naught plus RT ln of K. And so if we're at equilibrium, delta G becomes 0. Okay, so what we can do is we can use delta G naught to solve for K. So let's rearrange this equation in another way. So we could rearrange it to say that delta G naught equals a negative RT ln of K. Right, we just take this term, subtract it. Right, because when G equals 0, Q equals K, yeah. So what we can also do is, if we wanted to solve for K, we could rearrange this again. We could do that, we could say delta G naught divided by negative RT e to the power equals K. Whew. Sorry, I did a lot there. So we divided by negative RT, and then we undid the natural log by taking Euler's number and raising it to the power. Right? So delta G naught equals negative RT ln of K, or e to the negative delta, or e to the delta G naught over negative RT equals K. So let's use this equation. Let's plug in the delta G naught. It's what, 2.3 something something something. It's just like pi, David. It's a little that you have a lowercase e on your calculator. It's technically with an e. It looked like it looks like Euler, but it's actually pronounced Euler. Yes, Euler is a Swiss mathematician from the Enlightenment. Thank you, Isaac. A little history for you. All right, so let's plug in from our last problem. Remember, delta G naught in the last problem was 27.3. Sorry, I'm a little crazy with the page. So what we're going to do, we're going to just plug that in. So we're going to say e to the 27.3 divided by 0.00831. Oh, oops. Yeah, 831, not 813. Times by 298 Kelvin. That should equal K. So 27.3 divided by 0.00831 divided by 298 negative e to the x equals 1.63 times 10 to the negative fifth. Now, do we have a way to check that answer? Do we have a way to check this answer for our K here? Reminder, this was the K for the reaction lead chloride solid breaking up into lead and chloride. Do we have a way to verify this value of K? Last chapter stuff, because what is this K? This is a KSP. So if you look at the table from last chapter, we can see and see if it matches. So let's look up the KSP for lead chloride. So lead chloride from the book, 1.7 times 10 to the negative fifth. What do we get? 1.63 times 10 to the negative fifth. That seems pretty good to me, right? That's really close. So you can use delta G to find K using this equation. And the other way works too. If you know K, you can find delta G naught as well. Right? So we can go back and forth using all of these ideas from our previous chapters. We can connect everything together. Okay. Cool. That's actually all I wanted to teach. So, yeah. What other questions do we have? We've got 15 minutes of notes, really like 25 minutes. Um, so I think with that, if I'm not mistaken, you can now do all of the homework. Yeah. Oh, thanks, Max. Really? Why'd you save it as an HEIC file? You didn't actually save it as a PDF. Okay, let's answer a couple questions. So homework is due on Tuesday. Yes, Bryce. How do we know if a reaction is feasible? Feasible is another way to just say that delta G is negative, so spontaneous. So feasibility and spontaneity are the same idea. Do notes in Paint. No thanks. This is the end of the notes for the chapter. So I think on Monday's stream, I will just answer questions. Answer questions from the homework. No, not the IB Chem reference book. We don't want that one. We just want the AP. The IB one is huge. I mean, I guess you could, but oh, possible is a tricky question. Isaac, if you want to upload it, you go right ahead. I don't know if everyone will use it though. Okay, so 31 it says to find delta G. You did. How do you know if it's possible? Possible is a weird wording. You got to be careful on the wording. Better would be to say if it's spontaneous or if it's feasible from thermodynamic standpoint. Basically, is it negative? Is delta G negative? If delta G negative, yes, the reaction will work. If delta G is positive, no, it'll go in the reverse direction. Yeah, so thermodynamically feasible is another way to say is it spontaneous. Okay, what other last questions do we have? Any of the homework problems you guys want me to do? Or we could just end early. I can't. I don't know what they're doing. They jumped up here earlier. Is that the same with the sign is reasonable? Yeah, whenever they ask you to comment on the sign, if it's a sign for delta G, we're going to talk about negative delta G means that it's spontaneous, positive delta G means non-spontaneous, a negative delta H means exothermic, a positive delta H means endothermic, a negative delta S means it becomes more ordered, a positive delta S means it becomes more disordered. I might stream League of Legends on Monday nights or Tuesday afternoons. That's when our high school team has their games. I might do something over the weekend. Who knows? I can text my wife and see if the kids are in a position that they want to come up. Reasonable for delta S. That depends, Lauren. It depends on the context. So if you do a calculation, right, if you're trying to decide whether something's reasonable, you're trying to decide whether it's going to increase the disorder. In other words, is it creating more molecules, right? A positive delta S indicates it's creating more gas. A negative delta S means it's becoming more ordered. And so you can comment on the reaction and say, okay, say you calculated the value of delta S. You got delta S to be a positive value. Does the reaction look like it's becoming more disordered? If so, then yeah, that's reasonable. If you got a positive delta S, but the reaction looks like it's becoming more ordered, then your value isn't reasonable and something's weird, something's wrong. Hopefully that helps. Tetris 99. No, I wouldn't play Tetris 99. I would play Puyo Puyo. Freaking own some people at Puyo Puyo. Okay, hopefully that helps, Lauren. Again, I'll be in the Discord from 12 to 2. That seems a little extreme, Isaac. That's an interesting thing. It might be right, though. Cool, thanks, Max, for sending that as a PDF. Yeah, there we go. Much better. Not a great picture. I can upload the document I used to print this. I'll do that. I can do that at some point. It's on my laptop, not on my home computer. IBbook says. Oh, that's interesting. Cool. Well, we know that K changes based on temperature. We can calculate that. Okay, cool. If there's no other last questions, let's see. I texted my wife. Oh, apparently they're watching a show and eating a snack right now. So I don't think they are, they're not interested in coming and saying hi. Sorry. I'll have them come by on Monday. Sure, Sammy, I can look at 47. Let me look at it. We've still got time. I've still got time here. Here, I'll do a problem, TJ. And then we'll end the stream. So let's see. Problem 47. So 47 asks, here, let everybody read it. There you are. So 47. Two possible ways of producing iron from iron ore are that one and that one. Which of these reactions proceeds spontaneously at the lower temperature? That's fun. So what you're going to be doing here is you're going to be, you've got to find delta H and delta S for both reactions. And then you need to plug in temperature equal, or plug in delta G equals 0 and solve for the temperature to figure out when they become spontaneous. So I'm going to copy these reactions onto my page, and we can dive into that and show you guys how to do that. So Fe2O3 solid plus 3/2 of a carbon makes 2 irons and 3/2 carbon dioxide. Okay, so what we want to do is we want to look up the delta H of formation values, and we want to look up the S, so the delta H naught and the S naught values. So look up all those. We're going to do the same thing for the second reaction. The second reaction involves adding hydrogen gas to get 2 irons again, but this time we're producing water. And again, we want to find delta H F naught and S naught. So we're going to look up all the values for those. We're going to look them up in our giant table. Yeah, this is a tie that TJ got me. That's why TJ's commenting on it. So let's see. As I'm looking, I've got the carbon value and the CO2 value. So the carbon is 0 and 0.0057. Right, we know that the elements are going to be 0 as delta H in their standard states. CO2, negative 393.5. And 0.2136. Iron by itself, 0.02731. Right? 0.0273. So this one's 0.0273. Okay. Fe2O3, negative 824.2. So a lot of this is just, looking up these values from the chart. It's kind of where a lot of your time has to go. 0.0874. Okay, so I think, I still need hydrogen and water. So hydrogen gas, 0.1306. Water as a gas, aka steam, negative 241.8. And 0.1887. Yeah, so these ones, I'm using the chart in the back of the book. And so the chart in the back of the book has S in, so these are in kilojoules per mole, and S is in kilojoules per mole Kelvin. So I went ahead and pulled the ones that were already in kilojoules. So what we need to do is we need to find the delta H of the first reaction, reaction 1. And we need to find the delta S of reaction 1. And then we need to find the delta H of reaction 2 and the delta S of reaction 2. Right, to do that, you take the products minus the reactants multiplied by the coefficients. I'm not going to show all that because I don't have enough room, but I'm just going to kind of type it in my calculator. So let's do it in Excel. Oh my gosh, you stupid. Sometimes Excel's really great, and sometimes it's stupid. We want it to be a number. Hey, no, Excel's awesome. So what I'm doing is I'm putting in the coefficients. All right, so that means here our delta H is going to be this number times the coefficient plus this number times the coefficient. All right, all of that minus this number times the coefficient plus this number times the coefficient. Okay, do some Excel magic here. All right, so so what I've done is I've just kind of I entered my formula and I did the same thing a bunch of times, and I got my answers. So this is my delta H for the first reaction, 233.95. My delta S, 0.279. Delta H for the second reaction is 461.5, and my S is 0.054. Okay, so both reactions are, it's AP chemistry, yeah. So both of the reactions are endothermic. Both of the reactions are becoming more disordered because they produce gas. Okay. All right, so now we got to find, well, what's the temperature when delta G equals 0? So our delta G equals delta H G naught, delta H naught, minus T delta S naught. So we want to find the temperature when delta G is 0. So quick rearrangement of this equation, if we plug in 0 here, and we add T delta S, we get that temperature equals delta H naught divided by delta S naught. Okay, so now we just plug in from our first equation, and we plug in for the second equation. So from our first equation, it's 233.95 divided by 0.279. And the way the units work, right, this is kilojoules per mole, this is kilojoules per mole Kelvin, and so the per Kelvin just turns into Kelvin. So if I pop my Excel sheet back up, it's just this number divided by that number. So one of them, whoa. Is that right? Did I do that right? Did I screw that up? Oh, I did. Ah. There we go. That makes a little more sense. That's what I get for trying to use Excel and being all fancy. So it's actually 98.8 and 0.1415. Hey man, it still works. It's still awesome. It's still faster than doing it all by hand. Okay. All right. So we do this for the first one. We get 838 Kelvin, which is not unreasonable. So that's the first temperature. The second temperature, 98.8 divided by 0.1415, we get 698 Kelvin. Right? So if we go back to the original problem asked which one of these reactions becomes spontaneous at the lower temperature, and so it would be the second reaction. So reaction B becomes spontaneous at a lower temperature. Cool. All right, hopefully that makes sense to everybody. Hopefully what I did makes sense. It's a lot of just kind of mulling through the problem, looking up all the values, multiplying by the coefficients, subtracting, getting the deltas, using those deltas into our delta G equation, and just kind of plugging in and solving. So, no, it's not at equilibrium. Okay, okay. Woo, let's take a step back. Okay. It is at equilibrium. Okay, so let me recap. What are we doing into this problem? This goes back to what we were talking about yesterday. We were saying that when delta H is positive and when delta S is positive, where are you, notes? Here we go. right? So yesterday we said that if delta H is positive and delta S is positive, it's spontaneous at high temperatures. And so when we use this equation, it's going to change from being positive to being negative once we get to a certain temperature. And so that temperature, that tipping point, is when delta G naught equals 0, which is equilibrium. Sorry, I misspoke earlier. And so it's the temperature for this reaction when it becomes spontaneous under standard conditions, because we're still using the knots. And so we want to know, because we're positive, we want to get the temperature hot enough that it becomes spontaneous. Hopefully that makes sense. So again, the reason why we plugged in delta G equals 0 is because it's delta G naught equals 0 is our tipping point from non-spontaneous to spontaneous for this positive idea. Hopefully that makes sense. If you have more questions, Lauren, just hop into the Discord later. Okay, thanks everybody for tuning in. Hopefully we learned some stuff. Hopefully this chapter's not too bad. That's what we plugged in, Lauren. That was our whole calculation. So once we knew the values of delta H and delta S of the reaction, we plug in G equals 0 because that's our tipping point, and then we solve for T. T, if we rearrange this equation, is delta H naught divided by delta S naught. Plug in the values, we get the temperatures. Okay, hopefully that makes sense. Again, if it doesn't, just hop into the Discord at noon and I'll be able to answer some more specific questions in a more one-on-one setting. You guys are awesome. Have a great day. See you on Monday. Enjoy your weekend. Oh, it's going to be a nice weekend.